welcome to a algebra tutorial, working our way through linear modeling. And in this video, we're going to talk about the line of best fit. So linear modeling is applying linear equations, slopes, writing linear equations, graphs, but trying to apply this idea of lines to data, situations, patterns, things we see around us. So what I've got here is some historical data I took for, from 1964 on to 2012. I took the gold medal winning times for the women's 100-meter Olympic dash, the race. And what we're going to do is I plotted them. We've got the table values here. We plotted the points. And we're going to draw a line of best fit. We're going to come up with a linear equation that seems to model the trend of what we see in. Okay. So if you notice, the first thing we want to do is actually see, do our lines seem to fit a linear pattern? So if we go to see, the first value here was 11.4, and then it kind of jumps down, seems to kind of jump around, so it doesn't exactly fit a linear pattern. However, line of best fit, when we draw a line of best fit, use that word, we're trying to talk about drawing a line that seems to run right through the middle of all the values. So if I was to draw a line of fit that seemed to kind of fit the general direction of this data, you want some values to be above, you want some values to be below, but I would possibly draw my line of fit just like that. There's a lot of points from my table that are really close to that line and seem to follow that trend. Some are above, and then some are below, and you kind of want the ones above and the ones below to roughly balance each other out. If I was a statistician, if I'm looking at this data, I do see one value here. Let me draw my line here. This value here seems to be kind of an outlier. It's pretty far away. Like if I actually threw this point out and even possibly this point out, everything else really fits really nicely along that line. So there we go. We drew a line of best fit. We've noticed a couple points in particular might be outliers, but we have some good data here to think about a general trend, a general data trend. Okay, so how do we actually turn that into a linear equation? Well, if you remember, to do a linear equation, now that I've got a line of fit, to find the slope, I need 2 points. And once I have 2 points, I can write any linear equation. So if you're doing a line of fit and you're doing it by hand, you want to find 2 points that seem to fit your pattern of data pretty well. And then you're going to use those 2 points to find an equation. So I'm going to look along here. I like this point. That seems to fit pretty well, so that's in the year 2008. So I want to use these values. And if I was going to pick another one, I might use this point right here. It's pretty close to the line as well. That would be 1984. So I've eyeballed my line of fit. And again, you can do this by hand with a ruler. But we've eyeballed a line of fit. We plotted our points. We're finding 2 particular points that we're going to use to actually write an equation for this line. Okay, so once I got my 2 points, there's 1984, 10.97, and then 2008, 10.78. There's my 2 x values, 2 y values. Let's find the slope of the line. So the slope, if you remember, we find, well, what's the change in my y values, and we divide that by what's the change in my x values. So with our 2 points that we picked, we're going to subtract 10.97 minus the y value, 10.78. And we're going to divide that by years. So 1984, how much did my years change? 1984 and 2008. Okay, let's pull out my calculator and find out what we got going on here. So 10.97 minus 10.78 is a difference of 0.19. And over that is a change of 1984 to 2008 is a change of negative 24. So another way to think about this, if I transfer my negative up to the top, is over a 24-year period, the time of the gold winning score, the gold winning time, decreased by 0.19 seconds. So it's not a huge change, right? These women are running as fast as they can, and there's just getting into fractions of a second in terms of how much faster they get between every 4 years. But we want to turn that into a rate, so let's do 0.19 divided by 24, and we get negative 0.00, rounded to 8 seconds per year. So we just found the average rate of change, or the slope, and I can interpret that as, I should have put seconds, let me write that down below here. Every year, if we average between these 2 points, the gold medal winning times decreased by 0.008 seconds per year. So not very much, right? This is a tiny, tiny amount. But there we go, we have a slope formula now. Now let's write an equation. I'm going to write a point slope form equation, and I'm going to use this point right here. So remember, point slope form is in the form y minus y1, particular y value, equals m times x minus x1. So we can use our slope to put it in for m, and we can use this particular x and y value from this point to write an equation. So here we go. We've got y minus y1, which is 10.97, is equal to the slope, which is negative 0.008 seconds per year, times x minus 1984. All right, we just found an equation for a line of fit in point slope form. I'm going to go ahead and just leave it like that because it's great. I could simplify it. I could distribute the negative 0.008 and turn it into slope intercept form, but this gives me something that I could use. And I now have a linear equation that models this line, and this line follows the trend of what we see going on for the women's winning times, gold medal times for the 100-meter dash. Now once we have this equation, we could go on further. We could say, okay, the 2016 Olympics are coming up. Can we use our equation to approximate what the value would be? What would be the winning time in 2016? We don't know yet. It's coming up, but we could put, let's actually calculate it out here. So let's say we want to know in the year 2016. I can put that in for my x value, and let's see what y value we get back when we do that. Here's the nice thing about an equation is we can use it to predict things and estimate things. All right, so we put in our particular value. Let's calculate everything on the right here. So 2016 minus 1984 gives me a change of 32 years. Now let's multiply that by 0.008, negative 0.008. .32 times 0.008. And I get to this point now. So we've got y minus 10.97 equals 0.256, 0.256. And that is a negative value, so negative 0.8. All right, my last step is let's add 10.97 to both sides. And we see that in the year, if I put in the year 2016, according to our linear model, times negative plus 10.97, we see that the gold winning time should be 10.714 seconds. So we used our equation to find another point. We just found out that, all right, in the year 2016, the winning time should be 10.714, assuming that our model fits really nicely. So we can even write that in our table here, 2016, 10.714. And it seems to fit, right? Decreasing 10.75, 10.78, they're decreasing by a little bit. Our model says we have a decreasing slope. We're getting a little bit faster every time. So there we go. It should take 10.714 seconds. I'll be curious to see what actually happens. Obviously, you can see that sometimes times are slower, sometimes times are faster. We could have someone go at breakneck speed and get 10.4 seconds. We don't know. But anyways, we're using our linear model. We're able to draw a line of fit that seemed to fit where our pattern that we see in our data, and we use a couple of points that fit really nicely to actually get to an equation. So hopefully that it gives you a good example of line of fit and how to actually come up with an equation for a line of best fit.